All right, in this tutorial, I'm going to show you how to download the radio spectral data that you've acquired with our large radio telescope onto your computer, and then I'll show you how to upload it from there into our graphing utility so you can look at the spectrum, and I'll show you how to interpret these spectra. In particular, how to measure the wavelength of the most redshifted component, and that's the key number that we need to build the rotation curve of our Milky Way galaxy. I'm going to share my screen. Okay, here we are at Skynet. I'm going to go to My Observatory, Radio Observing. We'll have a list here of your observations. Here are my observations. 2 of them are still out. They haven't been completed yet, but I have a bunch that have been completed. I actually have a full set here of all the spectra that I need for this lab that have been completed. And you'll have to download each one separately. So let's go to the first one. This will take you to a page that has a link to Green Bank Observatory. We'll go collect the data from their website. This is their summary page of the data that you collected. Different graphs, different files you can download. What we're interested in is the calibrated spectrum, so right here. If you click on it, you'll see it's just a text file, but you don't even have to click on it. You can right-click on it and save link as, and that will download that text file onto your computer. It's going to go into my download directory. I'll just save it. Here it is. Get rid of that. And next, we're going to go to the plotting tool and select the spectrum option. And when you go here, you'll just see some generic junk data. We're going to overwrite it by uploading data that we acquired. So click on the Upload Data File button. It's taken me to my download directory, which is good. That's where I save my data. And the files all begin with the name Skynet. So if you need to search on Skynet, unless you changed the name of your file before saving it. And you can see I have a bunch of them in here. And I'm going to start with GL0. That's what I named my file for galactic longitude 0, for looking down the Bohr site at the center of the galaxy. Okay, now when you load in the spectrum, you should see emission lines. So bumps in the upward direction. If you don't see anything, if it's flat with nothing there, it means the channel's probably dead. These are complicated pieces of machinery and electronics, large radio telescopes, and they require constant maintenance. So occasionally we will lose a channel, but we do have 2 channels. So we can go to the second channel, and you can see it's basically the same thing. So if channel 1 is dead, go to channel 2. If they're both dead, tell your instructor, and we'll have to send out a maintenance team and repair the receiver. Anyway, back to channel 1. What are we looking at here? This spectrum is a little different than the others. There's a lot going on here, so I want to take a minute to explain it. Galactic longitude 0 means we're looking towards the center of the galaxy, and so we're going to see emission from every arm of the galaxy between us and the center, and then on the other side of the galaxy as well. And those arms, when we look at galactic longitude 0, we're looking at them perpendicularly. None of them are moving towards us or away from us. They're either moving to the left or to the right. So they're emitting this 21 centimeter line emission, but it won't be red shifted or blue shifted because it's not moving away from us or towards us. It all adds together to give us one broad emission line, and that's right here. Now you're looking at this and you're saying, well, I see 2 emission lines. In reality, this is 1 emission line. Let me show you the figure from the lab where I've kind of filled it in. We have 1 emission line, but on top of that we have an absorption line. That's because along this line of sight, there's some extra stuff going on. We're looking right at the center of the galaxy, and at the very center of the galaxy is a supermassive black hole. about 4 million times the mass of our sun. And around it is a disk of gas, clouds of gas that it's torn apart, stars that it's torn apart, and this black hole is feeding. And this disk of gas, we call it an accretion disk, and it generates magnetic fields, and some material gets shot out along these magnetic fields. We call these astrophysical jets, and these jets make a lot of radio waves. So in addition to the 21 centimeter emission, we're getting broad continuum emission from Sagittarius A star, from this system at the center of our galaxy. And some of that continuum emission is being absorbed by the very same clouds of cold hydrogen gas between the center and us. So these clouds are emitting a broad emission line, but some of them are absorbing light from the center of the galaxy, from Sagittarius A star. So we have a broad emission line and we have an absorption line right on top of it. In fact, you can see another absorption line over here towards the blue. It's been blue shifted. And this has to correspond to a cloud of gas that's moving towards us. And so it absorbs, but it absorbs blue shifted. Anyway, you can ignore the absorption lines. And this is the only spectrum in your set where you're going to have them, because this is the only spectrum where you're looking at not just cold hydrogen gas, arms of galaxies, but a bright radio emitting source. Okay, so for each spectrum, you need to measure its most redshifted component. And here we just have one emission line. And so you want the peak of this line. And again, we can't see it because there's an absorption line in the way, but the peak's probably lined up here as well. So this right here, the peak of the absorption line is 21.1053 centimeters, and the peak of the emission line is probably the same thing, right around here. So it'd be 21.1053 centimeters. Okay, that's along the line of sight to the center of the galaxy. Let's load another one. Oh, let's look at 48 degrees galactic longitude. So here we're no longer looking at the center, we're looking off to the side. We're intersecting multiple arms of the galaxy. And these arms, each one is moving towards us or away from us at different relative speeds. So we get an emission line for one arm, an emission line for another arm, an emission line for another arm. Each one of these bumps corresponds to a different arm of the galaxy. And this is the one that's most redshifted. So find that most redshifted peak and find the highest point right there. And so its wavelength is 21.1080. You want to say 4 decimal places. Okay? So this one's nice. The arms are cleanly separated. Let's load up one more. And I think let's look at galactic longitude 16. So here's an example where the arms are not cleanly separated. We have emission lines on top of each other. Again, we want the most redshifted. And I bring this example up because it's not always the highest point. In the last spectrum, the highest point was also the most redshifted peak. But here, the most redshifted peak is not the highest, not the brightest. And that's what you want. You want the most redshifted one. So this one appears to be 21.1141. Of course, this is the data I acquired. You'll acquire your own data, and the value should vary a little bit because Earth is going around the sun, and that adds a small velocity shift. So sometimes these data are just a little bit more to the right or a little bit more to the left. And that's something you can talk about in your sources of error. Anyway, the last thing I want to do is put a title on this chart and axis labels because you're going to turn in one of these. I think the last one, galactic longitude 88. So a good title would be Spectrum of Galactic Plane. Spectrum of the galactic plane. at this particular one is 16 degrees longitude, something like that. And on the x-axis, we're looking at the wavelength in centimeters. The y-axis, this is a brightness or an intensity. The technical term is spectral flux. Okay. Again, this is just 16 degrees longitude. I believe the lab asked you to save a different one, but this is basically how you make the titles and the axis labels. And again, you can save it here. Okay, that is it for this video.